Hi everyone. In this work, we present a data augmentation-free unsupervised learning for 3D point cloud understanding. This work is a joint collaboration between the University of Technology Sydney, the University of Trento, and Fondazione Bruno Kessler. In this paper, we present an approach to extracting features for point clouds without a label information. Given a three-dimensional input point cloud, our goal is to learn a mapping function between the three-dimensional input space and the d-dimensional output space. This without any supervision from either classes or label in the input point cloud. Existing approaches can be classified into generative and discriminative methods. FoldingNet is a generative-based method which leverages on a graph-based encoder and a folding-based decoder to deform a canonical 2D grid onto the surface of a point cloud. However, it has two main drawbacks. It is sensitive to transformations, and it's not always feasible to reconstruct the shape from pose-invariant features. Point contrast belongs to contrastive learning approaches, in which a point cloud is sampled by two cameras to get two partial point clouds. The two partial point clouds also share overlapped parts. After transformation and feature extraction, we get the feature vector of all the points. Then, contrastive loss is applied to tackle positive and negative point pairs, in which positive pairs are just the overlapped parts and the negative pairs are the other parts. Also here we have two main drawbacks. It requires many negative samples to compare and heavily depends on the choice of negative ones, and it depends on the data augmentations. In contrast, our first goal is to design a data augmentation-free unsupervised learning approach to avoid the inconvenience of building chains of ad hoc combination of data augmentations. Second, we develop an unsupervised method that is not based on global features, but instead can optimize local features, which facilitates the network to learn 3D spatial geometric information of point clouds. Therefore, we propose an unsupervised method that can be used for both rotation-sensitive and rotation-invariant networks. The output of our work is SoftClue. Our method first sends unlabeled data to a backbone and segmentation head to predict point-wise labels. Then, a cluster module is applied to produce pseudo-labels. Finally, a cross-entropy loss is used to train the backbone. We generate pseudo-labels based on two assumptions. Cluster cohesion, if a point belongs to partition, point and prototype should have the shorter distance among the distances with their other prototypes, and the uniform distribution. Each point cloud is assumed to be segmented into equally sized partitions of elements. More into details, SoftClue consists of three steps: prototype computation, soft label assignment, and optimization. In the prototype computation step, we compute J prototypes. During the soft label assignment, we use the computed prototypes in the SynchronOp algorithm and compute our soft labels. Finally, during the optimization step, we optimize the network by using the previously computed soft labels. We evaluate our approach on multiple downstream tasks of classification, parse segmentation, and semantic segmentation, and with multiple backbones. On classification, our method outperforms all the counterparts that adopt the same backbones. On ModelNet 40, our basic point and a backbone achieve better classification accuracy than a model generating model and contrastive approach STRL, which is pre-trained on a larger dataset ShapeNet. Notably, the linear SVM classification performance of our method even surpasses the performance of the fully supervised PointNet, which trains to 89.2 test accuracy from random initialization. Our DGCNN-based model achieves a 91 test accuracy, 91.9 for precision, outperforming the second best PAR AI. Our proposed method also attained competitive results on the ModelNet 10 dataset, which further justifies the effectiveness of our method. Our method improves the sparse segmentation performance and exceeds the baselines, Jigsaw and OCO, in terms of OI and MIOU. For PointNet, our pre-training improves the performance by 1.1 OI and 1.6 MIOU compared to training using random initialization. Our approach initializes DGCNN backbone, achieves 94.7 and 85.4 MIOU overall test accuracy, and it outperforms the random initialized DGCNN by a large margin. It is also slightly surpasses the second best OCO initialized DGCNN. For segmentation task, we can draw the same conclusion. Here, we report some segmentation qualitative results. On the top left, we reported TSNE process network features, where we can see that our approach on the right obtains better clusters compared to the OCO features on the left. On the top right, we report the PCA projection of the learned features. Finally, in the bottom figure, we report the qualitative results in the part segmentation downstream tasks. In this work, we propose a general unsupervised point cloud pre-training method. The method comprises three key components: prototype computation, soft label assignment, and optimization. Our approach is independent of any specific neural architecture. Thank you for listening, and check our GitHub page for the source code. Any feedback is appreciated.